Yes, now we are live. Let's wait for others to join. We'll wait for a couple of minutes. In meantime, people can join. Okay, in the meantime, I will start. Good evening, everyone. Welcome to our ML Math Club event, day 5th. Let me introduce myself. I am Sarita Shukla from TFUG Ghaziabad team, and I will be your host today for the session. And yeah, today we have an exciting session planned for you folks. There we will be discussing about the dimensionality reduction of PCA mathematical opus by Hrishikesh. And yeah, let me give you a brief overview for our agenda. So we will start the presentation by our speaker, and then it is being followed by the Q&A session where you can ask your question and queries in our live stream chat box. Okay, I can see people are joining. Okay, let me introduce our speaker. We have Hrishikesh Yadav in our session, and he is a esteemed AI and backend engineer specializing in all applied generative AI research in the company Saga. And he's also being a Kaggle expert twice and active member at Super Team DAO, and he's holding an ample year of experience in the same field. So today he's sharing about all the AI technology, all the latest steps that all are going on, and the innovation in that space. So yeah, I'm welcoming you, Rishikesh, to share your knowledge today. It's over to you now. The stage is all
Yeah,
yours.
yeah, thank you. Um, I hope everyone would be excited to explore a kind of a new way about mathematics. And I guess PCA is like the most favorite thing for me. And you will get to know by the end of the session why I am saying that. Uh, because anytime whenever you will be stuck with the data, okay, whenever you are dealing with the huge data, at that time the only thing which would help out is PCA. So it was a kind of a short intro of what we would gonna do. Let's have a look about the table of content. So we will be discussing about the real world application, what you can build, why we are actually looking towards this. We would be discussing about the applicative side, also visual intuition. Why visual intuition? We'll see to that. Then what's the mathematics behind that, and also the tips and tricks which I gathered while working on that, and also will build uh, a kind of a PCA. We'll try to implement what we learned. So yeah, that was all about the table of content. Uh, yeah, so I'm an AI engineer at Shaga Labs. I majorly work around the applied generative AI research work, mainly in the sector of criminology and policing tasks. So like I have worked on as in on the product as Crime Dekho, which is for Rajasthan Police Department. Uh, yeah, that was all about myself. I hope you are not in this mood and it won't be that uh, like you won't be that bored because I will try to have memes in between which would be related to that. Okay, so let's directly jump to the real world application. So here you can see the data set which you can see here, right? df.head, and in df.head you can see 5 rows and 399 300 and 3199 columns. So now you might think of like so many columns. Okay, how to deal with this? And this is just to let you know, this is the actual data which has been collected by the IIT BHU by their master's program for understanding about whether the planet is habitable or not by looking towards this flux which has been actually gathered. So this type of data is held for the exoplanet habitability classification. So whether that planet is which has been found or been studied uh, is cap- capable for humans to live in or not, like that. So this is like one of the use case, okay, where you can understand like when there are like lot many variables, lot many columns, then what to be done. Okay, so this is one thing. We'll discuss how to do that. I'm just sharing like what are the issues when you need to think about PCA. Then second, it have a lot much application in the gene expression, or if you are working as in biology plus ML or biology plus data analysis. There is a very big field in biochemical, specifically if I am talking about European region. So if you are working as a data analysis or any contract with the European companies, they would gonna deal with this pharmacy kind of thing. So this is like class discovery and class prediction by gene, and you can see there are like the attributes which we can see and about the gene expression. And here also it's 78 columns. So we can't just directly give 78 columns, right? We need to do something to compress it, okay, or reduce it. But the problem which comes with the reduction uh, is that it can lose their information, and we also need to retain the information, and even it should have a lot much of understanding about what is going on inside. um, okay, so third application is iris data classification. So this is like the very famous kind of a classification, which we will be doing. We will be also building around that. So it's like about three flowers, uh, where we have various features for that flower. Okay, this sepal length, sepal width. If you know, then the flower have a sepal or petal. So with the help of length, width, which are the actually the feature of that flower, we can identify or classify the species. And here you can see the number of column rows is 150, and column is only one, two, okay, five columns. So we will be working with this small one, but now you might be thinking of, okay, so we were trying to compress it, right? So why small data? It works very well for non-supervised, or I can say unsupervised learning data. So we'll see to that. Now, any other way out to work on this? If you might know, you can just write in a chat box. I can check. Like if I just provide this to you, what methodology would you take? Uh, can you guess? I'm right now checking the comment section. Like if I just provide this data to you, what methodology would you gonna think of? Because PC is the one thing, but there could be other ways too, right? Okay, I can't see any chat. Okay, no worries. We'll discuss it during the session. Um, so, what is actually dimension which we are discussing about here? So, it's about feature. Okay, if I'm talking about 3,199 columns, I'm talking about the feature. I'm talking about the dimension. Okay, because when you will be plotting, let's say you have two feature, you have two columns, you will be plotting in a 2D plot, right? But if I talk about 3,199 dimension, I am talking about. Okay, so for an example, let's say, so let's say if I am talking about the feature of a person, so it could be height, weight, or age. And now we have three feature, three column, which is three dimension. And if you need to plot it just to see or just to analyze, what you would do, you would make three dimensional plot, which is very kind of a difficult to take a judgment on what's going on inside that. And if we increase one more feature, it becomes 4D, and like it becomes very much complex, and it becomes complex for the model too to understand about what is going on. So yeah, here I can see in chat, Hitesh wrote like checking correlation. Yeah, great. Correlation works very well. You can just have a top correlated model which actually influence your target column. Okay, so if my target column in that application was whether the planet is habitable or not, and the feature which influences the most can be selected for that. Okay, great. Okay, so this was just a basic intro about what is dimension. If you might be wondering about whether it's we are talking about Marvel Universe dimension or something like that or not. Okay, why dimensionality reduction, like we are discussing about? Because it simplifies complex data. The problem is retaining the information to. It also helps to visualize high dimensional data, as I told, like how you can just visualize 4 dimensional or 10 dimensional, or you can't take a judgment on that, right? What's going on in that? So it works very well for the two, and it removes the noise and redundant features. Okay, so what are noises is which influences your accuracy, because accuracy, or which are like not actually useful to take a judgment on. So you can just reduce the you can just remove that and can actually enhance the accuracy. Also, it speeds up the machine learning algorithm to train on. So these are some of the advantages of making use of that. Okay, so as we were talking about PCA, like as a session title you might have seen till now. So PCA is principal component analysis. So we'll just going a bit into that very basic side. Let's assume principal component is a straight line that capture most of the variance of the data. अगर मैं ऐसा बोलूं कि प्रिंसिपल कंपोनेंट, इफ यू माइट नो लीनियर रिग्रेशन, या आपने जो प्रीवियस सेशंस देखे हैं, तो लीनियर रिग्रेशन क्या करता है, या फिर वो एक बेस्ट लाइन बनाने की कोशिश करता है जिसमें सारे पॉइंट्स सूट कर जाए, तो एक प्रिडिक्शन लाइन जैसा हमको मिले। तो सेम it works with principal component, जहाँ पे वो ज़्यादातर वेरिएंस कवर करता है। विल ट्राई टू सी इन अ ग्राफिकल मेथड कि क्या हो रहा है, बट वो जितना आप समझ लो कि एक स्ट्रेट लाइन बनाने की कोशिश कर रहे हैं जिससे हम ज़्यादा वेरिएंस कर रहे हैं, वेरिएंस से ज़्यादा इंफॉर्मेशन रिटेन कर पा रहे हैं विद द रिडक्शन ऑफ डायमेंशन। ऑल्सो ये जो प्रिंसिपल कंपोनेंट होता है वो वेक्टर होता है, इट मीन्स उसमें मैग्नीट्यूड और डायरेक्शन है। एंड ये जो होता है वो ऑर्थोगोनल प्रोजेक्शंस होते हैं। ऑर्थोगोनल प्रोजेक्शंस आर लाइक perpendicular. Okay, so uh, okay, you can see in the next in visual intuition about what is orthogonal projection and why it is not similar to the linear regression or the regression line that we have seen till now. um, so okay, so why visual intuition? So इट्स लाइक कि आप ग्राफिकली देखोगे कि क्या हो रहा है उसके अंदर, बिकॉज मैथमेटिक्स इज ब्यूटिफुल इफ यू सी इट विजुअली कि कैसे क्या चीज हो रही है टू मेक मोर सेंस अबाउट दैट। तो एट दिस मोमेंट वी वुड गोना सी कि हर एक स्टेप में या हर एक प्रॉब्लम ये क्यों कैसे पीसीए सॉल्व कर रहा है विथ ग्राफ्स। तो ओके, सो लेट्स से यहाँ पे हम स्टार्ट कर रहे हैं। अभी तक हम समझ रहे थे कि क्यों पढ़ रहे हैं हम, या क्यों समझ रहे हैं, क्यों कब काम आएगा हमको। ओके, सो प्रॉब्लम फॉर्मुलेशन ये है कि दिस आर सम ऑफ द डेटा पॉइंट्स विच वी हैव। ओके, ओके, कैन यू टेल मी what dimension of plot is this? Like you can write in chat box. What do you think? Which dimension it is, and and after reducing on at which dimension we can convert it into? We can write in like comments. So it's, you can see it's x1 and x2, which is 2 dimension. Yeah, 2 dimension. And how? And after reducing the 2 dimension, we can convert it into 1 dimension. So we need to convert this into 1 dimension. Okay, this is the main problem that we will be seeing with graphs. Next step, the thing which I was talking about earlier, that it is orthogonal and perpendicular. Okay, so when we used to draw the linear regression is the regression line, and regression lines are like the plot, like the error that we used to do as per that. But if you will see in PCA, we do perpendicular, okay, from the point to collect more variance. Why? Because if we just use this one, the x the x1 part is been preserved, the information is preserved. But for the y here, this is not preserved because we are doing this. But while doing perpendicular, we are compromising a bit with x1 and bit with x2, but we are retaining more of an information. That is the reason it's perpendicular or orthogonal, we used to say. If you have like any doubt here, we can just see in a very different way. But this is the main, very major thing which differentiates PCA a lot. Uh, okay, so here we have drawn that. Now pick the direction which minimize the projection error. So this is the direction which we got. And this direction is also that on which the data vary the most. So here this line, so this line which you can see here, the blue one is PC1, okay, which is principal component 1. And this line which you see here, the green one, is PC2, which is principal component 2. So what happen is principal component 1 captures a lot of information, okay. Then comes PC2, which contains a different information. So if we are talking, so let's understand here is, if I am talking about two dimension, so we are having PC1 and PC2. If I am talking about only one dimension, we are only talking about PC1. So it, you can understand about the number of principal component is equal to the number of dimension. So that is one more important thing which you can like note about. So yeah, it was about the mathematical intuition side. I guess the part of why and how it works like would be more clear to you. If you have like any doubt, you can just pin that. Um, Now, this is only the part of visual, right? Now we need to calculate it because we need to implement that. So for that, like we need to do this all stuff by using the process of mathematics. So we'll just see the what's the mathematics behind the magic which we were seeing. Uh, Okay, so what does actually PCA algorithm takes? It takes the number of dimension to retain. Okay, so like if it's two dimensional and the number of dimension you want to retain is only one dimension, so at that time you can just do that. Or and also you need to have a proper training set, particularly for that, particularly for the dimension which you are actually provided. So that is the most important or crucial part here. Uh, so majorly, what you can think of is you need to have like the number of dimension, and particularly here I'm talking about 2D to 1D. Okay. Um, there is also one more thing before actually implementing the PCA algorithm is you need to process the data, prepare the data. In a very similar way in which we used to do while building the machine learning model. Uh, so for that, we we need to standardize the features. So if you know about standardization, I can just annotate here. Okay, I don't know why it's not showing the feature here. Okay, so if I just tell you about the standardized, so it's a bell-shaped curve. Okay, so what happened? Like why there is a need of standardization? Let's say I'm having a column of a close price of a Bitcoin. It ranges from let's say 5 rupees, if I'm talking about, to 5,000. So there is lot much of variance, a dispersion. So to have a more sense about the dispersion, what we can do is we can just uh, kind of compress it and with having a mean of 0 and standard deviation of 1. So this condition actually makes it a bell-shaped curve, having a lot much of information in the middle part which contains f around like standard deviation one contains 75%, and then the next 95%, and then 99%. So if I just show you that, I can just I can annotate. So I will just present to you that graph. Wait. Yeah, can you see here the thing which I was talking about? So here it is. You can see mean is 0, uh, and here is the dimension. Here is the standard deviation, which you can see the standard deviation. It contains more of an information here. Okay, which is around 75% of an information. So yeah, that was what I was talking about. Let's have a look at what after that. Okay, so standardize each feature of element, which are actually numerical for the respective featured standard deviation, normalized data matrix. So it's like the same. Now comes a very important thing, which is singular value decomposition. So I would like to ask, like, whether uh, the people who have joined, like, have you worked around or know about what is eigenvalues or eigenvectors? Because it would help me to understand about to go from more scratch from eigenvalues, or we can directly understand about what are the major application of singular value decomposition and how does it actually work. So have you ever during the college or anything, like, have you came across an eigenvalues or eigenvector? Because like it was a part in, I guess, 11th 12th also. Yeah, Madhur is saying yes, that's really great. And if you will just, okay, so the best part about eigenvalues is, um, okay, there are like hundreds of, sorry, thousands of applications of eigenvalues. The mobile phone here have an eigenvalue. The surface or the wooden plank have an eigenvalue. Even the human body have an eigenvalue. So what is that? Eigenvalue means the behavior of that atom, or we can say the behavior of that material. Okay, because there is a vibration on each and every object. And for a fun fact, in oil mining, the vibration is sent through the land, and after that the reflection of that voice has been collected, and it has been studied the with the help of eigenvalue which has been collected of the oil, whether there is an oil inside the land or not, whether they should drill there that on that position or not. So you can now understand about like how much important it is and how many application it can be used into. uh, so for a single value decomposition, okay, let's come to single value decomposition. We will, um, 1 minute. I will just write about how you can actually calculate. Um, we will actually write down the whole mathematical part, how it works. Till now, let's understand about the terminologies first. So what all things we discussed about? We discussed about the standard scalar, we discussed about the SVD. Okay, SVD is remaining. Then about eigenvalues or eigenvectors. So about singular value decomposition, so you might have seen about the related to the applications which actually reduces the size of your image. Okay, you have an image of MB, it converts it into KB. So at that time, uh, some or the other way you can build with singular value decomposition. What it does is, it, by doing the calculation with the equation which you are seeing right now, is USV transpose. By just using this equation, you can get the x bar. Okay, in x bar, the diagonal position are like non-zero, and that contain the information of the image. So let's say I provide my image, which contains 200 rows. 200 rows of a matrix would give me 200 diagonal points having the sorry, having the non-zero values, which means any number, and that number is actually the information which is stored. So let's say what I do is I re- I just only restore 50 top, okay, 50 top row uh, singular value, and I just scrap all other. Still, my image is bit blurry, but a lot of what we can say, a lot of size has been reduced. So let's have a look at the example first. Um, Decomposition. Uh, I will just show you how it actually looks like. Yeah, I going to create example, and then we'll see the main how you can just try to solve or implement. Um, where is that? Okay, I'll just one more. Yeah. So here, this is actually a good example. Uh, we could have like just build the this code. I have like the code source. I will just provide that because of like bit time constraint. We can just discuss the example here. So let's say this is the image. Okay. Currently, you might be seeing all the images in the Google why they are in a grayscale, right? The reason is if I am talking about grayscale, we are talking about the two dimension, and that's why we can plot it. If we talk about the colored image, which is RGB, it is three dimension because we are talking about red. There is a red matrix, then green matrix, and blue matrix. So for an easier mathematical calculation, the two-dimensional images, which is a grayscale image, is being used. तो यहाँ पे आप क्या देख सकते हो कि ये जो इमेज है, ये वाला इमेज जो है, उसमें 20 सिंगुलर वैल्यूज है. ओके, n is equal to 20. It seems clear, right? Now I change it to 15. It There is kind of no change, like very small change I can say. But when I did 10, it becomes more blurry, and at 5 it becomes more often blurry. So here we are compressing it. Also, the information is also getting lost. Okay, so this is the important part. So this is like very less or more of an less pixelated. So that's why here with a small change it happened. Let's see this one. So so if you will just see this, here it is 264. So it means the matrix is of 264 rows having 264 diagonal points having numerical value. Then in 262, you can see there is no difference. In 260, there is no difference. 251, no difference. 251, no difference. Okay. When I just compare 264 with 202, there is kind of no difference. So, but it got reduced. We just, the residual or the rows which are having less information, like we just reduced that. And then you can see the lot many got reduced. So this is a kind of an application of SVD, but SVD is a kind of a stage in while developing PCA. Okay, so this is a one step, but this step also have a very much application. Um, then comes what we are doing is this V1, V2, VD. तो ये सब we are collecting, and these are all principal component. And what are principal component जो हमने पहले discuss किया, PC1, which is the first in this list. The first principal component would represent 1D. The second, first and second would provide us two dimension. So if you just understand like that, so it helps to reduce the matrix, which we can see here. And the thing is, now the question which comes to the mind is, oh, sorry. I guess my screen, you can't see my PPT. Yeah. So we were here, right? So in PCA algorithm, here you can see the list like V1, V2, and VD, which is the principal component. And V1 is like the first principal component, which so so yeah, like it all contains like eigenvector, and also we calculate here covariance matrix. So covariance matrix is to actually gather about the information retention from that, and the focus is on to have the maximum or most of the variance as we discussed earlier. And then we calculate like principal component score, which is like projected by having a z and the x bar, which we got from here. Okay, so there you got to know, okay, why svd came into the picture. And also, if you might be wondering about the v2, that is the value which is being calculated by. Okay, so first step is you have a data, you have a two-dimensional data, you calculate eigenvalue, eigenvector, and then you just set in the SVD and all the data which is being collected, which is VT here. Okay, uh, and this U and S is like different parameters which you get, and after implementing that, you get X bar. After that, you just put that X bar with VQ. Okay. Um, so VQ is the reduced matrix that we got uh, after like or like we can say while applying the PC uh, with the help of like after calculating the covariance matrix with the eigenvector. So or and also it is like you can just recover the original data by just an approximation uh, by just computing with z dot vtq, and the z is the principal component score. Okay, the higher the score, the more you can retain to, or we can say approximate, but it actually looks very same. अब यहाँ पे एक और क्वेश्चन आता है, हाउ यू डिसाइड कि कितना प्रिंसिपल कंपोनेंट अच्छा होगा. ओके, और like कितने डायमेंशन रिड्यूस करूं, बिकॉज इफ यू आर टॉकिंग अबाउट 2D to 1D इट्स नॉर्मल, राइट. बट इफ यू आर टॉकिंग अबाउट 3199, अब उसको मैं कितने डायमेंशन में कन्वर्ट करूं सो डैट कि वो ज़्यादा अच्छा एक्यूरेसी दे हमको. um, so for that there are modules present in Python in which हम कैसे उसको समझते हैं कि कौन सा प्रिंसिपल कंपोनेंट कितना ज़्यादा वेरिएंस कवर कर रहा है, कितना ज़्यादा इंफॉर्मेशन रिटेन कर रहा है. एंड व्हेन यू सी द नी पॉइंट इज जितना मतलब लाइक wait if I just so okay, so this is the knee point. The first one, and with the help of like eigenvalues and dimensions. So let's say if the first one contains the lot and second and third, now you understand this is the knee point where it goes a lot like below that. So we would just consider two of the principal component or the eigenvalues to actually calculate the principal component. So that was the part. We'll see more things further. So एंड ऑल्सो लाइक हमने जो डिस्कस किया था कि इनपुट में ही हमको देना पड़ता है कि कितने डायमेंशन हैं. सो सो डैट कि वो बाद में चेंज नहीं होता. तो हमको ये सब एनालिसिस पहले करने पड़ेंगे, डिस्क्रिप्ट प्रोसेसिंग वाली चीज़ें बहुत पहले करनी पड़ेगी. Okay, I can see some question here. Why is it necessary to center the data, subtract the mean before applying PCA, and what could happen if we skip this step? Shikha, yeah, really great question. Actually, it's there in slide, but I will just hop onto that slide. It's actually really great. So I know that this is like people would ask about like why standardization. So the reason is uh, all features doesn't contribute equally to the target column. Okay, some features would contribute more, and we are only talking about the numerical columns. So if we just standardized, we can actually have a strong hold on the variance, and that would help us to actually classify in a more accurate way. Okay, so that is the reason why z-score standardization is used, and that is also the reason why in many application it has been converted, like the data has been standardized or is converted into Gaussian type of a part. uh, okay, so you can just have a look around, like if in a more way. So here you can see, we can just have like three principal component with the standardization. And also, like, there is one research which I can show to you. Wait 1 minute. There is a really great paper. um right now, I don't know why. Research. So the thing is, the paper actually said that PCA works under the assumption of like the data is whether the not normal distributed, and it is actually very much sensitive towards the outliers and also the variance, because it's actually taking into account about the information, right? So that is the reason. So I get, like, it's clear like why we are doing that. Also, I can see one more, like, what are some common pitfalls or challenges one might face when applying PCA to real world data set? Okay. Uh, so the problem, I guess, if you know about the more problem would be if the data sets are more of an categorical, or mix of a numerical plus categorical, but it holds a more value or influence towards the target column. At that time, I guess it would be very much difficult. But and also, like, if it's not standardized, or if also if your data contains outliers, so having a bit of an EDA around data set and analytics would help you to proceed further for the PC implementation. And as soon as you just compressed or reduce the dimension to get the features, uh, that's the best thing to have the most accurate model around that. So yeah, I guess your doubt is clear. You can, like, ask anything related to that if you feel like. Okay. So as I told about that, the okay, sorry, I can share the screen. So it have a very huge impact in the criminology sector. Okay, to actually identify which area is prone to which type of crime, and there are like lot many features. If I just talk about the data of Karnataka police, it contains like 40 plus categories of crimes, and like on a global level, it's a standardized format. Chicago police also works in the same way. So uh, there are like lot many other dimensions which comes into the picture. So the data set which you are seeing right now is the USRS data, uh, which contains the research paper actually took very less feature here, like the state. Here you can see Alabama, Alaska, and there are like some features of murder, assault, or the population of that area, because it matters a lot, the rape cases. So what you can see here is it has been the okay. So just let me know, like, how many dimension is there in this section before converting. how many dimensions you can see. You can write in like numbers. Okay, so if you can just let's say avoid state, or if you just include the state, it's 5 dimension. Okay, so and it has been converted into 3 dimension, but we don't need to take consider the state. Okay, because that's not numerical, right? Also, one more thing which is needed to be considered here is uh, understanding. Like here we can understand, the other way out is like correlation, which we can see, but here we can understand like murder, assault, and rape have a kind of a very similar kind of an relation as compared to urban population. So what can be done is, like, we can just group that and urban population to actually generate the features. So let's say after compression we got this PCA1 and PC1 and PC2, and when I plot this, okay, this is component 1 and this is component 2, and as I told about, component 1 contains more information. Here you can see this is the zero axis, okay, and these are all the data points. And as I told before, this principal component is a vector, so you can see magnitude and the direction of it. Um, so here for murder, you can see 0.05 or zero point 0.4, which gives to this, which means nearby Alaska and South Carolina, there are more often murder cases, and the urban population goes towards um, like New Jersey and that location. So this actually helps us to understand like lot much of data and numerical sense to actually make a conclusion around that, like about what is actually going on here. So like Mississippi have like less things or activities going on, like particularly South Dakota and Vermont to Iowa. So these are the regions where like kind of no crimes are happening related to this. So also one more thing, they have a less population there. So that is also what we are getting to understand. So by just having like 4 dimension, by converting to 2 dimension, we are still we are and even in a better sense, we are able to understand about what is going on. So that's the really great part here. Uh, if you have like anything here, you can just write about that. Um, yeah, so that was like one more use case. So till now, if you might be counting, we have like seen around 4 use cases or actual why. So now you know why PCA could be the best thing you might explore. Um, okay, so the tips and tricks part, which is kind of the issues or the thing which I got to know after like working around PC a lot. The first thing about the standardization that we have discussed. Okay, yeah, okay, okay. There is some more thing. The as per the question of Shikhar, there are like more things is which is if you don't do the standardization, and then when you plot it, you will see in this way. Okay, in this you can see the only the first one contains a lot much of that, and the second one doesn't, and the other part. Also, this could be the reason of an outlier. uh, so that's the part. And when you actually do the standardization, you provide like the equal opportunity for them. to understand whether it actually influences the target column or not. So here we can just take like two, or like we can just take three. Okay, so that's why standardization is important. Um, Second thing here is like PCA is sensitive to outliers, so it's very important to handle them first, because we are talking here about variance. We are talking about here the distribution. Okay. While talking about variance, we are talking about the dispersion of the data. So it's important to identify and like remove or transform the outliers, and like considering the robust PCA technique for like if there is a noisy data. And the major thing is visualization tools helps us to understand about the outlier. So here you can see, if I just took this plane, which is a three-dimensional plane, you can see there are lot many points here, but there are few points very much above the plane or below the plane, not exactly where it should be. And when we just convert it into orthogonal distance and the score distance, we can actually identify that PCA maps there. So that's the major part here. Also, the thing which we're discussing earlier was about this screen plot, uh, about the eigenvalues against component number. So we need to look like if we can just put around the principal component or eigenvalue, but if we are looking towards the more accurate model to build on, it's helpful to actually plot and understand about the elbow point, so that we can, if we just take a 3, it's good, but taking a 2 would give a more better. So it's important to component before elbow explain most like variance about that. There is also a trade-off of information. If you reduce more, if there is a 5 dimension, you convert it into 1 dimension, then more of an information would be lost. So setting a threshold and the balance between the dimensionality reduction and information retention, it's it's very helpful. Like it would help for the better performance. एंड फिफ्थ पार्ट जो यहाँ पे आता है कि पीसीए जो है वो फीचर इंजीनियरिंग है. ओके, इट्स नॉट ओके. सो देर इज अ वेरी मच डिफरेंस बिटवीन द वर्ड रिडक्शन. ओके, बिकॉज रिडक्शन मतलब ऐसा नहीं कर रहे हैं हम कि वो फीचर हटा ही दे रहे हैं, रिमूव नहीं कर रहे हैं. वी आर ट्रांसफॉर्मिंग इट. वी आर doing feature extraction. Okay, so there are two things. First is feature selection and second is feature extraction. Feature selection is the part which like someone wrote in the chat about that. Like feature selection is about taking the most correlated features which actually influence the target column, and and just throwing away or dropping away all the other features of that data set. And the second is feature extraction, where you actually transform four features into two features. तो यहाँ पे या फिर हम बोल रहे हैं कि दो डायमेंशन को एक डायमेंशन में कन्वर्ट कर रहे हैं, तो वहाँ पे एक डायमेंशन को लॉस नहीं कर रहे हैं, हम ट्रांसफॉर्म कर रहे हैं. So that is the thing, yeah. So combined with original features for better model performance. And ये ज़्यादातर यूज कहाँ पे होता है? Most of the time, most or like all the time, with image processing or signal analysis. Still, you can make use of that into a tabular columns, having a numerical values and all. Yeah. One more thing here you can see is principal component. This contains more information than PC2 contains. So that is the part that we have discussed earlier. Uh, so I guess we'll have a look at hands-on, and if there is anything, we'll discuss more in the Q&A section. I will just paste down this code of mine into the chat section. You can just open it. Um, Wait, I guess this one is not live. 1 minute. I will just make it live and share it in the YouTube chat section. And then we'll have a like it's a small code to build PCA, so so that we get the kind of implementation of how it works. So just it's a version code. Like there is no need of kind of version. Okay, we can just have a this code only. It works.
If there is any issue, then you can send the link to me. I will paste it in the chat section.
Yeah, I guess I am unable to paste on YouTube. I have pasted in the this the other part. You can just share it too. Uh,
Okay,
and
after
also
it.
I will, yeah, I will just share the screen of the link, so how you can access and make use of that. So this is just a starter pack, okay? So to explore. Um, so we just have a quick through of all the steps that we have seen. So kernel is just starting. You can just click on edit the notebook, or you might be getting the option of poking it or something like that. Uh, Wait, I will just show that around. Like what would you see in on your account and what to do. Okay, so you can just poke it from there and edit the notebook, so you can be on this stage. I hope like you have got the link and also in this
Yeah, I
position.
have pasted that in the
Okay,
YouTube.
okay, cool. So after like starting the this, we'll just import like few of the modules here. So pandas for the data manipulation. NumPy is very useful here because lot many mathematical calculations have been present. Seaborn and Matplotlib is for the data visualization, which you can see. So there is like iris flower dataset, which you can see, which we were talking about, sample length, sample width, and petal length. And the species which you can see here is iris setosa. So, and if we just do the value counts, we can see there are three species: setosa, versicolor, and virginica. And all the three classes are being distributed equally. So if we just see the columns, we can just have a look at the columns with just df dot columns, where we can see like sepal length, sepal width, petal length, all that stuff that we have seen earlier. There is also one more thing which you can do to have a look whenever there is a situation related to this. You can just write df.info and you can just see 150 non-null. Okay, so it means like the whole data is complete and having like float and the species having the object. So object here is like the string. So अब यहाँ पे हम क्या करेंगे? So what this does, dot ilog star and 0 to 4. So यहाँ पे the thing which you need to understand the most is The first thing in this list is represents rows, and the second is the column. So rows मतलब ये बोल रहा है कि सारे रोज ले लो. Head shows only top 5 rows. तो मैं बोल रहा हूँ कि सारे रोज ले लो, बट कॉलम आप क्या लो, 0 to 4. 0 to 4 is 0, 0, 1, 2, 3. Okay, excluding the species. And that is the reason यहाँ पे हम 4 ले रहे हैं, सिर्फ 4 ले रहे हैं which contains the species. So with that, it is the target column here, the column which we need to actually classify or predict. um, and we have like lot many features similar to the way like if you need to classify a human by any category, so you have like as we saw like age, weight, height. So we have 3 dimensions. Here we have kind of 4 dimensions of the features. So here, here it's just a plot. Okay, so it's just a graphical representation of how it is being distributed. So what you can understand here is each thing shows with color. So blue color is for setosa, ऑरेंज कलर वर्जिनिका के लिए है और ग्रीन कलर जो है वो वर्सी कलर के लिए है. what you can what you can see here is 4.5 से ये 5.5 तक है, और यहाँ पे बहुत सिमिलैरिटी है लाइक सेटोसा और वर्जिनिका का जो है ना, बहुत सिमिलर आ जा रहा है. एंड देन यू कैन सी वर्जिनिका एंड वर्सी कलर के अंदर बहुत सिमिलैरिटी है. फॉर सेपल लेंथ, इफ यू सी पेटल लेंथ, यू कैन सी ये बहुत ज़्यादा अलग है सेटोसा. देन कम्स वर्जनिका और वर्सी कलर, एंड ये तो बहुत ज़्यादा सेपरेटेड है पेटल विथ में. बट इफ यू सी सेपल विथ, तो ये अलग है. सो हियर व्हाट यू कैन अंडरस्टैंड इज द डिफरेंट फीचर contributes in a very different way to classify the class of that flower. तो यहाँ पे the major step which actually enhances the accuracy of the model is standard scaler. तो हम क्या करेंगे, हम सबका स्केलिंग सेम कर रहे हैं. व्हाट वी आर एक्चुअली डूइंग इज वी आर हैविंग अ मीन ऑफ 0 so that it have a bell shaped curve, and सारा ये ट्रांसफॉर्म हो जाएगा हमारा. Now, the second part comes is we calculate covariance matrix. Covariance matrix से हमको क्या पता चल रहा है, जो information retention होता है ना, कि we aim for a maximum variance, okay, for more information, तो वो भी हमने यहाँ पे कर दिया. There are other ways to implement this. You can just directly import the module, but you would never get to understand what's going in the background. So ये हम पूरा scratch से बनाने के बारे में देख रहे हैं कि what are all the hidden things which are going on here. And that is the reason why the numpy is being used, because it contains a lot many things. You can just implement covariance, um, covariance here, and std is the transformed, that the 4 features is being transformed into standardized. Standardized is like in having in -1 to 1 value kind of in that space. And it is also been transposed here with just writing dot t. Now the thing comes is finding out eigenvalues and eigenvectors. If you might have seen earlier, eigenvalues has been calculated with uh, a lambda and v lambda, and their lambda is actually the eigenvalues which has been calculated. And also there is an identity vector where you try to make it similar, that the A matrix which you have, you try to make it make your identity vector like having only the position filled with the non-zero value at the diagonal position, and you transform the identity vector to. It would be better if I just write about that. But currently like an iPad, like there is no way to share screen, so uh, wait, still I will just try to show you um, like how it actually looks like, and then we'll just proceed. Okay, good. I got a good example here. So if you will just see this example, let's say I'm having a matrix of 1, 4, 3, 2, and how I can just calculate eigenvalue is I will take the determinant of a minus lambda I, or if you will just see, it's actually a is equal to lambda I also. Now what I will do is I is identity matrix. Okay, identity matrix is like having a zero value all other places and non-zero value, which actually the unit vector of like one kind of is present in all the diagonal position. So uh, 1 minus lambda and 2 minus lambda, and here it's like 0, and with the help of that we got the eigenvalue of pi and minus 2. Now if we just see about the eigenvector, so for eigenvector we have ax is equal to lambda x. So if we just see here, in previous we got lambda, right? So the same way here, like we got the lambda as 3 and 1. Now the next step come is ax is equal to uh, like vx, or we can say the lambda. So it's just like 1 minus 1 minus 1 1 which we got here, and that x is like the variable which you have. And after that we got the eigenvector, and as per this step that we have discussed earlier, the eigenvector is being used for the calculation of singular value, and singular value contains the most of the information, mostly related to images we apply, but here we are applying at the tabular data. So yeah, that's all. We just need to import linear algebra and dot eigen to covariance matrix. And here we got all the eigenvectors and all the eigenvalues. So we got four eigenvalues here. The most or the highest number or value of eigenvalue stores highest value. Okay, so here you can see 2.93. Then we have a drop here of 0.92. Then we have a drop of 0.14. So it would be best if we go for two dimension here. I guess this behavior is visible because of the type of the uh, influence of that feature on the target. So, okay. So if we just calculate the correlation matrix, um, okay, it's here we just calculated with the covariance matrix. Here the correlation matrix. Again, values are same. Okay, so then we need to have an eigen decomposition. Okay, uh, based on like the correlation matrix that we have got, and here we are just implementing on core mat 2, uh, and everything is stored in eigenvalues and eigenvector, and that is not much of a difference you might notice. Okay, let's jump to singular value decomposition. You can see how easy it is. Like you make use of NP, which is an alias of NumPy, then linalg, which is linear algebra, dot SVD, and then the standard deviation dot transpose, and you get the SVD here. Okay, which contains a lot much of information which has been retained. Now there is a need of pairing it. Okay, so this is just for a testing of with the transpose, because all the metrics needs to have like the proper dimensions to move further for the process. Um, so there is a need of making a list of eigenvalues and eigenvector tuple, uh, and then sorting the eigenvalues and eigenvector from high to low, because we prioritize more to the high because it contains the most, uh, what we can say, higher information retention, so that we just don't lose too much of an information while reducing it. Still, we are not reducing it, we are actually transforming it into a more optimized way. And then comes the total, where we just sum up all the eigenvalues which we have here, and then we just calculate the variance of, and here like we get this. Now we'll just plot all the this thing with principal component and variance ratio. Here you can just have a look around the knee point stuff, and you can still take consider of like two dimension is best here to go for. Okay, let's say if the knee point is 20, or we can just understand like third one is like too low. So we'll take two dimension. Okay, we'll just reshape it. I guess why there is an issue. Okay, there is kind of happened which would, there is a loss of something. Um, um, okay, I guess I forgot to run any cell or what? It passed. Wait 1 minute. It passed. So it's here. No, I ran this cell, ran this cell. Sometimes it behaves weird, this kernels. So yeah, here we got the matrix of that shape, and here we just do a dot product with the two metrics, the one which is standardized and the second one which is the metrics that we just did here for the two this for the two principal component. Okay, and now we'll just print in the two dimension here of principal component 1 and principal component 2. You can actually clearly see the Setosa class is well defined, like well classified. There are a lot many similarities with the features of versicolor and virginica, and that is the reason. Like, if you will just see in a higher dimension, there would be a large difference around that. If we just see in a three-dimensional way, but in a two-dimension, there is bit of a kind of, we can say a area where both coexist. Okay, but still we are able to do that. So this is the way of mathematics, and if I just summarize that part is uh, taking the data, understanding how much dimension you convert into, you need to reprocess the data with standardization, then calculate the eigenvalue, eigenvector, then go to singular value decomposition, and after all the eigen decomposition, you just need to just pair up eigenvalue and eigenvector, then understand about which principal component holds the most, and then you just do the dot product and all stuff, and you can just plot around what the feature, the two dimension that we have converted here. We just use that. Now, if we just talk about the libraries which I have, which we have, like you would be shocked when you will get to know that this can be implemented by just 3 lines, all this stuff, but that doesn't contain the mathematics side, that doesn't contain the logic behind that. So we will just go to sklearn. Sklearn is like scikit-learn library which contain the decomposition part, which is kind of a transformation. For a lot many reasons, you will explore decomposition. In that, there is an PCA and there is a scale on PCA. So here in n components, you can see 2, which means we are trying to convert into 2 dimension. And here dot fit transform, which we are doing with xstd. So the thing which in the upper code remains the same is the standardization of that 4 features. And here, tada, bar, we got this, and we can just directly plot. So if you are trying to learn, you can firstly do this part. Okay, and which is the most easiest, and you will be making use of only this only while implementing. Okay, all that stuff is just the behind of the work, and actually you can build your own module around that and any modification if you wanted to do. And this code is just very basic Seaborn code, so I just didn't took much. It's just like x, what to write on x label and y label, and the location of the legend, which is on a upper center, and the layout dot show, and about the colors. So it's just a configuration for the visualization. So here we can just clearly see like lot many features which are influencing in a very 2D way. So yeah, I hope like it's been clear about what is PCA and about like how it's like useful for the various application. Um, yeah, so yeah, that was all about like today's talk, and you can just reach out to me if you wanted to discuss about something or related to anything or related to Gen AI or ML. Yeah, thank you everyone.
Well, thank you so much, Rishikesh, for this insightful presentation and covering all the foundational aspects. Um, okay, we will move on to the Q&A. We have few questions. If those are answered, then yes. Okay. If those are answers, then yeah. Thank you everyone for all the questions and the active participation. We hope that you found the answers helpful and you got all the queries cleared. And yeah, we have dropped the social handles of Rishikesh, so you can just go and check it out and all the socials. And yeah, we also have uh, feedback form in the comment box, so do fill that out. And yeah guys, this video will be live and on our main channel, so you can check it out and you can share it with your friends and peers, and you can also connect Rishikesh on his socials. And if you have other queries or questions, you can just have a one-on-one with him. And yeah, for all other queries, you can follow us on our socials, on our TFUG socials platform. And yeah, before we wrap up, I would like to remind you all guys, like we have our other upcoming events that will be followed on our weekends. So we will look forward to seeing you there. And yeah, once again, thank you for joining us today. Have a great evening ahead. Thank you. Thank you,
Thank you
Rishikesh, once
everyone.
again. Yeah.
Yeah, thank you.